What if the rules of matter were more fluid than we ever imagined? That's the mind-bending question at the heart of a recent discovery in materials physics, one that challenges our understanding of how materials behave at the quantum level. While the practical applications might not be immediately clear, the findings are undeniably fascinating and could pave the way for future breakthroughs. Materials scientist Lou Lee and his international team have uncovered a peculiar phenomenon related to quantum oscillations, a behavior where electrons in metals act like tiny springs, their vibrations influenced by magnetic fields. But here's where it gets controversial. These oscillations, once thought exclusive to metals, have been observed in insulators, materials that typically resist the flow of electricity and heat. This raises a crucial question. Do these oscillations originate from the material's surface or its inner bulk? From a practical standpoint, a surface-based origin would be more exciting. Scientists are already exploring topological insulators, materials that conduct electricity on their surface while remaining insulating inside, for their potential in next-generation electronics and quantum technologies. But Lee's team, utilizing the world's most powerful magnet at the National Magnetic Field Laboratory, has found evidence pointing to the bulk as the source of these oscillations. It's a remarkable phenomenon, Lee admits, but we're still grappling with its implications. We've documented it, but its practical use remains a mystery. This discovery, published in Physical Review Letters, involved a diverse team of researchers from the US and Japan, including Lee's colleagues Quanwen Chen, Yuan Zhu, and several graduate students from the University of Michigan. Lee frames this work as an exploration of what he calls the new duality in materials science. The old duality, established with quantum mechanics over a century ago, revealed that light and matter exhibit both particle and wave-like properties, a concept fundamental to technologies like solar cells and electron microscopes. Now, Lee proposes a new duality, materials that can behave as both conductors and insulators. To investigate this, the team experimented with Ytterbium boride, YBB12, under an incredibly strong magnetic field. Their findings challenged the conventional view of surface conduction in insulators. The idea that we can harness a conductive surface for electronics is simply wrong, Lee explains. The entire material behaves like a metal, despite being an insulator. However, this behavior only emerges at an extreme magnetic field strength of 35 Tesla, far beyond what's practical for everyday applications. While immediate applications remain elusive, the discovery opens up a wealth of questions. How can we replicate this behavior under less extreme conditions? What neutral particles are responsible for these oscillations? As Zhu notes, confirming that these oscillations are intrinsic to the bulk is just the beginning. We hope our work inspires further experiments and theoretical advancements. This research not only pushes the boundaries of our understanding but also invites us to rethink the possibilities of material behavior. Is the line between conductor and insulator as clear-cut as we once believed? The answers may lie in the strange and exciting world of quantum oscillations, waiting to be unraveled by curious minds. What do you think? Could this new duality lead to revolutionary technologies, or is it a fascinating dead end? Let's discuss in the comments.